First of all, good evening, everyone. Someone in the audience pointed out that only I know that the color is wrong, so you should just pretend the color is right, and there's no issues here. As Greg mentioned, I'm co-founder of OODA Health, which is about a year-old company, year and a half in San Francisco. A whole other talk on what OODA Health does can be maybe a future talk in March or later. We do AI and automation in healthcare claims processing, trying to make basically healthcare experience more like a retail experience when you're how much you owe and payments are done to the providers, etc. Just out of curiosity in this audience, does anybody recognize the acronym OODA? John Boyd, wow, okay, deeper reference even. Yeah, OODA stands for Observe, Orient, Decide, and Act. And it's an old term that comes out of the Air Force. Lieutenant Colonel John Boyd coined it. And that's a whole other interesting story. That's not the topic of our talk today. I am borrowing a few slides from my co-speaker at Strata, Troels Erting. Troels was my colleague at Barclays Bank in London. He was basically in charge of security globally across the bank. He is now, interestingly, at the World Economic Forum. They created a cybersecurity, global cybersecurity center. He heads that up. And the whole notion behind this is to take what we did at Barclays and turn it more global in terms of cost. I kind of reserved the right to change a little bit from the advertising of what I was going to talk about. So I will focus more on the utilization of data fusion with AI and machine learning, and more importantly, the importance of data. And that's a whole other talk we can give around big data and how to utilize it correctly. Yeah? So ransomware is when you effectively take over systems, and it's typically done to data, and you do something like either delete the data or more commonly encrypt it. And you send your poor target a message saying, if you want your data back or the password to decrypt it, send this much in Bitcoin. Many, many companies, many banks keep reserves in Bitcoin because it is cheaper typically the offenders than to try to fix the problem. So this is an epidemic in a sense, right? So it's kind of, and we'll talk towards the end around why this is open season, how it's happening, and how bad it's out there. In fact, it's so bad that you can pretty much rent crime as a service on the internet, on the dark web. So you can actually go somewhere and you say to somebody, oh, I want to buy an attack on this company that I don't like. So here's a few $1,000s. Why don't you orchestrate anything from something simple like a denial of service attack to something much more, much worse. So and examples of that are Wikileaks as an example. That's definitely a violation of information security. And again, the numbers are staggering, right? So 3 billion documents a year leaked on average. So it's a scary environment out there. If you think about security, followed by Canada. By the way, there is a reason why these guys are the biggest. Like, does it surprise you that Canada is second biggest in the world?
Yes.
Yeah, that is surprising, but part of the explanation is the problem is much worse elsewhere in the world. The rest of the world is not as open about it and is not willing to admit, right? So that's why you'll see things unusual, Canada being so big. I am sure in terms of actually providing tools, now not intentionally, and we'll talk about a few examples here, but unintentionally or intentionally, these tools wind up in the hands of the bad guys, and they end up getting used in unanticipated ways. So that's another thing to think about, which is another reason why it's hard to fight this fight. Because if somebody's doing it for the government, what are you going to accuse them of? Like Stuxnet is a perfect example of this, right? That technology was developed by the NSA, and the purpose was to attack nuclear reactors in Iran, right? That then got leaked and started getting used against US companies. Let's hope this is not stuck. Second one is integrity. An AI technology, scientific research, the videos are pretty amazing. One is Obama speaking, the other is the AI speaking on behalf of Obama, making his lips move correctly, making the sound incredibly like his sound, to the point where it's extremely difficult to tell which one is the real thing and which one is, actually when I looked at it, I thought the fake one was Obama. But of course, it was unbelievable to hear what was being said. If you're curious, you can actually check this out. It's still on the internet. But the point of this is, this is a highlight. This is highlighting integrity, which means when you see something, when do you know that you can believe it or not? Is it real or is it fake? And that's the big question. And the third one, which is extremely important, is privacy. The biggest one for me is the personal, right? And you contact people on chat. It knows your location at all kinds of time. If we had time, I could do a demo to have you look at your iPhone log of where you've been. Pretty scary stuff. Your travel plans, what you read, news, etc., what you like, your contacts, what you search for. Access to this means access to you and your family and often your work. So this is, if there's one slide that should scare you a lot here, it's this. And a lot of the technologies we will be talking about are actually designed to attack this. Right? With Cambridge Analytica and the Facebook data and Facebook sharing data about you, etc. And what happened there in April, there was a notification of 87 million members, data leaked. But that appeared to be the start of a trend. So in June, there was a whole other disclosure around 120 million users. And if you think that's the end of it, 2018 is the most recent one, which actually in many articles has been called the biggest hack in history, because basically people were able to hack the credential system. You know how you use OpenAuth to authenticate yourself at different sites using Facebook? Well, guess what? 50 million accounts got compromised, including the one for Mark Zuckerberg and Sheryl Sandberg and several executives. So this stuff is happening all the time and happening at an alarmingly fast pace. So how do we fight these threats? Right? And this is how we're going to lead up to why we need data and AI. Well, the industry tells you patching, right? Patch your systems. And security patches are the answer. Anybody here heard of something called zero-day attack? Zero-day attack, in my opinion, is one of the biggest jokes in the industry. So what is a zero-day attack? A zero-day attack is when you actually first discover that there's a vulnerability in a system, right? Now, these are some interesting statistics here that kind of measure how long that vulnerability in a typical company has been sitting there before the hack is discovered, right? So day zero, time zero, is when, say, Microsoft or Oracle or somebody announces, hey, we actually recognize there is a vulnerability. And the typical scenario is anywhere from minus 60 weeks, minus 40 weeks or so, that vulnerability has been sitting, undiscovered, right? Until you call it zero day. What happens when you call it zero day? Typically, a patch is released, typically about 10 to 15 weeks after the fact, right? So now imagine this T0, even if you believed it, that suddenly now it's known, it's documented that there is this vulnerability. And now the manufacturer has released a patch. Now, how long do you think it takes to deploy that patch in most companies? Right? On the average, the number we see is almost 40 weeks. So here's what's going on. From minus 80 to plus 40 weeks, you're living with this thing. Right? It's a vulnerability. It just hasn't become very public. The people who know about it are few, but usually those are the dangerous guys. And this goes anywhere from kind of script kiddies who, you do it for bragging and you just show that you can do stuff, but all the way to very sophisticated, very deliberate efforts by nation states and sophisticated cyber gangs who are doing this on purpose, right? So you might hear a lot about the script, what we call the script kiddies. You don't hear too much about what's happening with the nation states. By the way, I mean, I don't know what else I can say to scare you more, but let's say you work on something of interest to somebody, like China. How difficult do you think it is to get some kind of malware on your PC and on your phone? And I'm not saying China is the bad guy. I mean, let's use the US, because I don't want to attack China necessarily. If the US decides that you somehow are working on something interesting, and I want to monitor what the heck you do on your computer, it is not hard at all to actually target you by name, through searches, through many things, through ads, and get something on that computer of yours, and now it's logging everything you do. So that's always a very healthy thing to do, to actually look for these things, keyloggers and other things that are sitting on your computer. Patching also is reactive. So what happened here in this cycle that I showed you is the thing gets announced, manufacturer launches a patch, waits for the market to deploy the patch, and now we're kind of protected, right, quote unquote. So the question is, how do we detect these things, right? Well, usually the detection is you look for a pattern. And these patterns usually are, you look for like files or droppings or traces of this malware doing its thing, right? So sounds reasonable. I'll write these algorithms that look for these files and these droppings, and that will give me a hint that at least I'm under attack. Well, guess what? It gets worse. So there's this thing now called fileless attacks. So the bad guys are pretty smart, and they're very adaptive, right? So now a lot of the news and a lot of the scary stuff is around what's called in-memory fileless attacks. So these things do not leave the droppings, do not leave the hints that allow them to even be detected to be at work. And we'll talk about examples of some of these things. And this is why it becomes really super hard. It's a very interesting detective problem to figure out how to detect when something bad is happening, right? Because these guys, essentially, this is like when you're hiding your traces. You're not leaving any footprints. You're not leaving any sign of you being there, right? So here's a scary chart with the help of my friends at Versec, which is a cybersecurity firm that I'm an advisor of. This is sort of the timeline of when we take, and we trace the root of all evil in cybersecurity to Stuxnet. Which is like the incidents that became very well known. But these things, not only are they changing in variety, to the far right, they are growing exponentially, and they are evolving from being the kinds of hacks that leave traces behind to the kinds of hacks that are basically in-memory attacks that basically try to corrupt your stack and make your function return to the wrong place, take over, replace files that are legal, right? So we'll talk about some of these where they replace a Python library or they replace a Windows DLL. Looks fine. When you look for it, it's supposed to be there. It's part of the system, except you're running not the original one, whoops, but the bad one. And we'll talk about some of these as we go through. So number one is it's increasing in variety and frequency. It's also increasingly harder to detect because it's going fileless. Here's another curve of kind of the popular ways to attack, right? And in this audience, I wonder, how many people here know what SQL injection is? Right. That is one of the simplest ways to attack, right? You have a web form where somebody is trying to maybe register for this event, right? And you ask them, type your name. So they type their name, but their name, they make it look like an incomplete SQL command of some sort. Because they know that this form is going to get sent, appended to a string, and sent over to be executed as a SQL query against a database to look up, hey, did this user come here before? Well, if I put something in it that looks like a command, when it gets sent to the server will execute it. And it typically says stuff like, select star from whatever, right? And starts dumping data right out. Now, what's funny is this is considered kind of the amateur early way of doing attacks, the SQL injection. And it started out as pretty popular in the old days. And it kind of died away. But really what's interesting is it's making a comeback in more sophisticated ways. So a lot of these things are actually not disappearing. They're just coming back in much harder ways to detect and deal with. So again, all sorts of different ways to kind of attack. And we'll look at a couple of these in the case studies. Here is why the problem is hard, right? If you think about how attacks get weaponized, it's the following. So you have traffic that comes to your company or organization or whatever that is good, right? Let's say for somehow, and this is not guaranteed, you can identify, you can authenticate somebody, and this is a good person, right? So this user, she's a good user, I want to let her in. Then there's, of course, the blacklist. There's a whole bunch of people who are known to be bad. And that's easy. We know how to block those guys. Anywhere from blacklisting them to getting smart around sending them to the wrong places. For a while, for example, distributed denial of service attacks, when people got the idea that, hey, I can block these things before they even reach your computer, right, through the content distribution network. That's a way to sort of block all the bad guys before they even hit you, and they never have an effect on you. However, what about the rest of the stuff? And the unfortunate problem is that space is exponentially larger than the known and known good and known bad. And that space basically is business as usual. This is traffic coming in. Which of it is bad? Which of it is not bad? Which of it is going to target my code, my interpreted code, like SQL injection is an example of interpreted code. Compiled code, which is when I go and change something in an executable, or microcode, which we will talk about at the end of this talk, is how do you actually attack the infrastructure, especially when we talk about critical infrastructure, and change effectively the ROM of the system, right? The microcode that's running the hardware. And there, no matter how many times you reboot and no matter how many times you reinstall an operating system, problem is not going to go away because it's in your microcode. So the bigger problem here is, imagine you're going to an airport, through an airport security, and your goal is to get a gun on board, right? You could put a gun in your bag, and probably the X-ray machine will pick it up. But if you took the gun in pieces and put it in different pieces of luggage, in your jacket, in maybe a buddy's bag, etc., none of the pieces look that bad. Once you're outside security or past it, you can reassemble this thing into a weapon. This is what's happening now to actually make this penetration possible, is people are actually doing it in parts, under different packets, different traffic, etc., and then assembling it on the other side. So all this stuff is happening, and the real question here is, how do I protect without disabling the business from functioning? All right, so my promise here is to connect AI and big data to this whole thing. So let's shift a little bit to AI and big data. And I'm going to ask you to indulge me a little bit. In this audience, about 6 or 9 months ago, I got invited to speak to a bunch of execs who, unlike this audience, knew nothing about AI and machine learning. And they said, just tell us what the heck this stuff is. What is real, what is not? We keep hearing about it. We must do AI, was the theme. So I actually did this thing that I thought was interesting, as a backgrounder to teach somebody who doesn't know AI. Then when I looked at it, I said, wow, this is even useful to me. Then I experimented with it with a few audiences who actually know AI, and they found my synthesis, at least, to be interesting. So this is going to be my view, my summary in a few slides of the whole field of AI, what works and what doesn't. So AI, very simply defined, the use of computers to simulate human intelligence. Very old concept. Goes way back, even before Alan Turing, in my opinion. But Alan Turing put in this thing called Turing test, which we have beaten many, many, many times. Then people thought that, like, chess players beating the world masters would be an amazing feat of intelligence. It turns out now the best computers beat the best champions routinely. But it's not intelligence, and we'll talk about that in a second. Games like Jeopardy, right? And you all know how Deep Blue basically beat Jeopardy. So the term AI itself was coined in the 1950s in a workshop by a group of people. Herbert Simon from CMU was sort of the famous guy for making it popular and coining it. But what happened was, there was a first wave back in the 50s when people had a gleam in their eye and said, oh, yeah, we can make these computers intelligent. There was a major underestimation of the complexity of common sense reasoning, something that we call it common sense because everybody does it. Everybody knows how to do it. Kids have common sense. Unfortunately, computers don't. So what do I mean by this? If I make a statement in this audience and I say, classic example in AI, elephants nest in trees. Should take you a few seconds to say, well, wait a second, this doesn't make sense. Elephant, big animal, can't really climb a tree and make a nest. That doesn't make sense. Getting a computer to do that is very, very hard, it turns out. And I'll give some reasons why. Natural language understanding, getting computers to talk the language of humans turned out to be much more difficult than we thought. We ended up solving it statistically, but not actually from an understanding perspective. And finally, mathematical logic, which was hoped to be a good representation, turned out to be untenable from an efficiency perspective. In fact, even from a decidability perspective. But where did this technology work? Well, it worked in extremely narrow problems where you had no need for this common sense, this evil common sense reasoning, right? Because typically, you know everything about the world in that setting. And we'll talk about settings like this, where you can know everything about the world, right? So many practical applications. You had expert systems, scheduling, travel bookings, game players. Games, by the way, are an excellent example of having a complete representation of the world. You don't need to know anything else other than the board configuration, right? In that world, the computer stands a chance to beat you, and in fact, it does. Then there was, so after this, AI kind of went through its first winter, died for a while. Then it came back. It woke up in the early 80s with neural networks, where now suddenly neural networks were going to solve all problems. We still had common sense reasoning. We couldn't crack it. We still couldn't make natural language understanding work. We still severely underestimated many problems that we thought are solvable, like machine vision. So even understanding what's in a scene, one still image, was very difficult. And probabilistic reasoning did not scale. So we went from logic to probabilistic reasoning, which was much more promising, but we couldn't at the time make it scale. What did we learn? Well, we learned a couple of pieces of wisdom. One is the problem was worse than this, right? This is what I said, referred to before, which is you seem to need to know everything before you can make a small thing work. And that's why we got limited to this whole idea that these things work really well when you have complete knowledge of the world. And that is where games fall. That is where a lot of business and engineering tasks fall, where you can actually basically know everything about the world, right? And then you don't need common sense reasoning. You don't need to kind of extend your knowledge beyond that world, and you can function well, right? And there was a lot of stuff that came out of this, including from Japan. Fuzzy logic became very popular. My favorite application at the time was they used fuzzy logic in cameras to do focusing, and they called it fuzzy focus.
And vacuum cleaners.
And in vacuum cleaners, indeed. Lesson 1. If you want to make AI work in an enterprise, reduce your problem domain to one where complete knowledge is possible. So make it as narrow as possible. And then it actually becomes suddenly solvable. Now, how about big problems, like machine vision? Right? You look for simplifications, and you avoid image analysis completely. Now, here's an example. You're checking out of a supermarket. I know now we have Amazon Go, but I actually went into the store the other day, and I don't know, if you, next time you go, take a look at the ceiling. And you will see a scary amount of sensors looking down on you. I don't know how Amazon will ever make its margins back from these investments. But let's say you want to say, what are the items in this basket? Right? Well, you can actually do it by you slap a barcode on each item. And now you can actually recognize this item in the dark at different angles, in different ways, faster than humans, more accurately than humans. Right? Here's the question. Does it have anything to do with how humans see or interpret a scene? Right? So the joke in machine vision for the longest time, when we hit our second AI winter, was like, oh yeah, we can solve machine vision by just putting barcodes on everything. Everybody will walk around with barcodes on their foreheads. And by the way, that's not very far from what's happening today with recognition and all of that. It's almost at that level. Nothing to do with how humans do it, yet a very effective engineering solution. Many, many, many solutions in AI are of that class. Nothing bad about them. This is a very elegant solution commercially, but it doesn't tell me about intelligence. So, hype around the 80s. None of the initial hype came true, right? In the 80s, by the way, there was this very scary program, probably Peter Friedland remembers it well, called the Japanese 5th generation AI systems, right? Lots of talk. Nothing came out of it. Today we hear about the China 2030, right? All the predictions that these computers were going to replace jobs, quite the opposite. They created a whole bunch of jobs, right? Whole new sets of positions. They elevated our level of interactions with many tasks. And one of my favorite quotes in the field is, in my opinion, when people are scared that AI is about replacing us with robots or replacing humans with robots, I usually tend to say AI is about taking the robot out of the human rather than replacing the human with a robot. So, familiar hype. Nowadays, you hear it from the likes of Elon Musk, right? We are all going to be jobless, brainless, and China 2030 is going to obliterate us. My prediction is not much is going to come out of that. It's like the Japanese 5th generation. Fundamentally, not because the rest of the world is a bunch of good guys, it's just the problems are really hard to try to get intelligence to happen, and that's why we should continue against the problem, and we should try to come up with solutions. Eventually, I think we will, but it's just a long way to go. Now, here's an exception. Both AI winters, one field in AI survived them. It's called machine learning. And this is going to take us into data now. So, machine learning is a subset of AI having to do with systems that basically change their behaviors once they observe data or events. By the way, the first and still most impressive piece of work in machine learning was done by a man named Arthur Samuel, who worked for IBM in the 50s. There's Mr. Samuel and his, and those are real computer tapes, and that's how computers worked back then. But Samuel had this beautiful idea. He liked checkers, and he was curious to see if he could teach his computer to play checkers against him. And sure enough, with a formula that scored the board positions, etc., he could get the computer to beat him consistently. Then he had the even further insight to say, what if I fed it all the championship games, right? What happens? Well, suddenly this computer started playing better than the champions in that region, in that part of New York. So to me, this is absolute proof that you could write a piece of software that can learn to do a task much better than you, the author, could do it. So there was no way Samuel could have cheated here. right? Which is why I like this. But in general, this is a theme that seems to have survived both winters, and in my opinion, will likely survive the third winter that we're going through. By the way, machine learning became critical in many areas. We all use search. It is a fundamental, core part of machine learning relevance inside the search engine. People think that Google engine was superior because it had PageRank as an algorithm that looked at the structure of the web. Guess what? Through machine learning, PageRank effectively disappeared. There's about 500 features that get scored, and PageRank is not one of them anymore. My favorite quote here, which is very accurate, is by my friend Peter Norvig at Google, who said, "We don't have better algorithms. We just have more data." And that statement is disappointingly very true. I am really hard-pressed to see, did we have really breakthroughs in algorithms in machine learning, say, from the 80s to today? Not really. But we do have a lot more data and a lot more compute. So you hear about deep learning. Remember I said in the early 80s there was neural networks, and people did a lot of work and said, well, these neural nets, we can actually reduce them to just a one hidden layer network. We don't need more. And they did a lot of theory about what they actually do. Now we actually have a new magic box called deep learning, which is these networks much larger, both in breadth and in depth. And basically, they're doing a lot of recoding and changing. And I know in a few weeks, you're going to have a talk on deep learning. But that's really the big change here, is you're just throwing a lot more data at it and a lot more computation and allowing the neural network to kind of discover new attributes that you don't know about, hopefully. This is one of the charts I like, because it sort of lists all the subfields of AI. And if you look and say, are we doing these subfields today? Most of them, you can strike through them and say we replace them with machine learning. And this is kind of a consistent hack, right? A lot of places where we used to hand code expert systems, now we do it by just learning automatically. You might hear about robotic process automation and other things. Translation, classification, and clustering, all these things got essentially replaced by machine learning algorithms, including machine vision, including text, well, I don't want to call it natural language understanding, but text understanding. So machine learning did survive this because it leveraged data. So where are we today? We have many practical and useful applications. There's a serious presence and opportunity. Recommender systems are everywhere, right? Can't get away from them, including in places like Netflix. Interesting stuff like Erica, Mathematica. Embarrassing stuff like Microsoft Tay. Has anybody heard about Microsoft Tay? Yeah, Microsoft is trying to wipe out that memory. 2015, they released a chatbot. And they put it out there publicly and said, hey, chat to this thing. It's smart. And I think it took like a few hours for a few hackers to figure out, hey, if we talk to this chatbot in a certain way and use certain language with it, we can now make it use bad words and not just social slurs, but racist slurs. So, of course, Microsoft quickly shut it up and pretended it never happened. And you can't find a trace of it. Promising and overhyped, like IBM Watson, which is now trying to get its act together. At the same time, I'll give IBM credit for what they've done with Deep Blue, which was amazing. Useful, map routing. Like I am addicted to, as much as I hate the implications on my privacy, I'm addicted to Google Maps. And it's really bad, actually. I mean, this thing is sending your position every 6 seconds back to Google. Yet we say, absolutely, why not? It's going to save me some traffic. And I love how Google handles it, by the way. They handle it in a very clever way. Google has a very nice policy. It says, if you don't want to be tracked, log out. But if you log out, I'm going to turn off these handy things like I'll remember which addresses you like to go to or to drive to. I'll remember your home versus your work. And we are so lazy, like including me, who is paranoid about privacy, that I still log in and say, damn it, remember my home address. So this stuff is actually very addictive. Radiology readers, for example, today, machines are pretty much reading almost all X-rays in the world, or at least in the US. Mobile apps with situational awareness, which can be scary. Okay. Promising, facial recognition, getting there. Alexa, beautiful approach with 40K skills developed mostly by the community. That's when you create a platform and you say program new skills into it. That's got its problems, but annoying. Unfortunately, I can take some credit for the fact that I made behavioral targeting mainstream when I was at Yahoo, and nowadays, if you like, God help you if you read an article about a certain topic or indicate interest in a certain product. You will see ads for that product for the rest of your life. By the way, when we created it, I had all sorts of guidelines around how not to use it, and they all got thrown into the dustbin of history. Lots of promise, autonomous driving, like tons of investments going into it. Unlike most people, including Elon Musk, I actually hold an opposite view here. I don't think we're going to see autonomous cars in the near future. I think it is much longer from here. One example I like to talk about is about a year ago, I landed in Chicago, pick up a rental car. And they didn't have the car I picked, so I was lucky. They upgraded me, and I got this Mercedes. And I love Mercedes. I have one of them. And I'm driving on the highway, and every time I pass a car, right? I'm passing a car, and it's on my right. This Mercedes slams on the brakes, right? So this happens for a few minutes until I finally park on the side because I'm trying to figure out how do I turn off this collision prevention. Now, being a natural intelligence, not artificial, and using my common sense reasoning, I realized that this thing, the sensors, were probably facing to the side, not to the front, right? Now, here's why I use this story. And by the way, like I said, I love Mercedes. I love Daimler-Benz. I think they produce some of the best cars in the world. This is Mercedes-Benz. Imagine how much testing this damn thing went through before it made it to the hands of a consumer. Yet, a simple thing like misaligned sensors fool it into becoming a very dangerous situation. Now, let me give you the analogy of a human. You wake up in the morning, and you're a little groggy, and you go to the bathroom, and you think you're looking at yourself in the mirror, except you're looking sideways, right? What happens to you? Right? It will take a few seconds to a few minutes for you to feel very dizzy, and knowing that, hey, I can't even leave the house, right? That equivalent reasoning has not been matured enough to be embedded in the machines we build nowadays. All right, financial advisory, drug discovery, where it's extremely promising, by the way, and doing amazing stuff, scientific knowledge compilation, the whole bit. So we said this is about the data, because we don't have better algorithms. So what do we do about getting the data we need? How do we deal with the velocity, variety, and volume of this data? New big data technology comes to the rescue. We call it big data, Hadoop, which also was developed by Yahoo and pushed into the open source community as a contribution. I never thought that we'd see it as the new, basically, default data infrastructure. But big data is a mix of structured, semi-structured, and unstructured data that typically breaks normal databases, relational databases, and typically requires intensive pre-processing before we can actually get any information out of this. This approach of big data was developed in association with search technology. And in fact, when we released Hadoop, we thought we were democratizing search technology. Turns out we solved many other problems. But what is interesting here to us is the following. How did it all start? Right? Why was this technology developed? Well, we needed to count keywords in billions of documents, now trillions of docs. Why? Because that's how search engines work, right? You count the number of times a keyword occurs, and you correlate keywords in a search phrase, the 2.8 keywords that you type, with what's in a document. Right? Everything is a bag of words. So I'm going to ask you a question. What was the earliest big data machine, in your opinion? Any guesses? PageRank.
How about the census gathering machine in 1890?
Somebody cheated here. It's a machine that looks like this. It's known as a Hollerith machine. And what year did you say?
I said 1890.
Very close. Very close. 1888. Census Bureau ran a competition. Basically said, if you can help me count the US population, which I'm required by law to count every 10 years, and do it fast, you win this amount of money. Now, what's interesting is he designed this machine, right? On the right here is a sorter that sorts treasury bills. And he figured out, he was inspired by train conductors and how they punch tickets. So he turned these into punch cards. So for the longest times, punch cards were the size of a treasury bill. Why? Any guess?
Because you use the same machines.
Well, because the Department of Treasury was having a sale on these machines, and they were trying to upgrade. So he bought the cheap ones. So for the longest time, this was the way they were doing counting really fast. And you know, this thing is very analog, but it works very well. He formed a company, called it the Tabulating Machine Company, and then went through a bunch of mergers. All of this is happening in New York. You know, it's amazing, actually, outside New York City. Computing Tabulating Recording Company is the new creative name. And these guys needed help in branding. So what did this company get called after it got rebranded?
IBM.
That's right. IBM. So these machines for counting fast, they were needed for a long time and for a variety of reasons, right? So data is a huge enabler of practical AI because of machine learning. So make sure your data is captured and managed as an asset. In most companies, data is managed not as an asset, but it's typically a liability because it's not used. It's there for exposure, and we're going to talk about data leaks and all that kind of stuff next. And you need to have a story for how do you grab all these new forms of data that traditionally we're not used to, like social media, documents, video assets, customer service recordings, whatever you have. So back to our code. We don't have better algorithms. We just have more data. So what are we doing with all this data? So if you're a bank, and now we're going to go into some of the examples, you care about this data, right? Why? Because 100 years ago, your business was pretty much branch-focused, very human-oriented. So the branch manager and or the staff pretty much knew everybody who walked in, you know, who was a good credit risk, who was a bad credit risk, who they are. Today, there's something called KYC for Know Your Customer. It costs a bank like Barclays 100 to 200 million pounds a year just to run a KYC program, which is just know who your customer is, what is their job, what is their address, what is their age, what is their gender. All the stuff that was known easily, you know, who's a good credit risk, who is going to go to college, who wants to buy a horse, who wants to sell their house, whose business is going downhill, was known. Today, it's called a risk function inside a bank. And in a bank the size of Barclays, it's typically like 300 million pounds a year. So a lot of these things became very, very expensive activities to just know who the customer is and how risky they are. And those are both like front office and back office. And this all happened because banks tried to scale, and they did scale. And they started going online, and they started creating lots of branches, et cetera. So what happens in a typical bank, this is just an example. I'm not going to read through it. You have a lot of events. Like people come in, they try to do stuff with your branch or online or on the mobile. Every event is a chance to learn something new about the customer. And every event is a chance to take an action, like decide what is the next best thing here. Should I help this customer find something? Should I pitch this customer a product, et cetera? That picture in almost all banks does not exist, right? Most banks are not as good as Netflix or Amazon at essentially reacting to these actions, these opportunities that happen all the time. And that's primarily because data is very hard to do for them. So lesson 3 for practical AI. AI and machine learning, they are very finicky algorithms. They expect the data to be in certain formats and in certain transformations. And they're very sensitive if they're not in that format. They're basically not workable, which means you need to have an infrastructure that not only allows you to capture all the variety of this data, but to transform it to something that is useful to these algorithms, which is lesson number 3 here, to make stuff work. And by the way, all of these things, if you pay attention to them, you can make the stuff work bit by bit and make it all come together. In a bank, for example, the average annualized cost of cybercrime is up 40% in 3 years, according to Accenture. Increased from 12.97 per firm million to 18.28 million in 2017, right? And many instances here of bad stuff happening. I've used some examples here. Banco de Chile lost 10 million in a SWIFT-related attack in 2018. India's Cosmos Bank was another famous one where they siphoned off a whole bunch of money and were actually willing to go a lot more. A spelling mistake in an online bank transfer helped prevent nearly $1 billion heist, right? Basically, the bad guys goofed on just making a spelling mistake. And so on and so forth, right? So the attacks happen a lot. So now let's talk about data fusion. So when I first arrived at Barclays and partnered with Trolls, he came to me and he said, you know, I want to capture every event that touches the bank, and I want to put it all in one place. And we wrestled for a long time because of 2 things. Number one is, this is a huge variety of data, huge volume, huge velocity. So typical big data, except in the bank, nobody knew how to spell big data. And bringing in new systems, especially open source, God forbid, into a large institution is not an easy thing to do. But we actually persevered and put together this system. By the way, the next thing we had to worry about is where the hell do you put this data? Because if you assemble it in one place and it gets hacked, you're done. So we actually went to amazing measures, including at some point going all the way to like an air gap architecture. What does air gap mean? Meaning you can't get to the system unless you're physically there, right? So there's a, and by the way, we will talk about ways to hack through air gaps. So it's a false sense of security if you think an air gap protects you. But in many places, people feel much safer if there was that. So we figured out how to build it. We put the data together. And the purposes were cybersecurity. We needed to know when an event happened, is there any other unusual stuff happening? Can we correlate with it? And then later, of course, many banks heard about this and wanted to share data and wanted the architecture. But what's more important also, or what's more interesting, is the minute word got out that we had this data in one place and we could use it and analyze it, all other functions in the bank started wanting to have access to it. So the fraud guys wanted access to it. This is credit card fraud and retail bank fraud. Financial crime, which is basically KYC or anti-money laundering. Marketing groups, risk, etc., several other groups. So that was pattern number one, is everybody wanted this data, because it turns out nobody had the data put together and made available to be used very quickly. And we call this architecture data fusion, which is the ability to identify, leverage, and analyze, and use information from a huge data lake. I don't like the term data lake, but via AI, and deliver actionable input to enhance intelligence, trends, patterns. But most importantly, is to enable human analysts to follow up on some events or some actions. So a lot of it is about filtering and saying, pay attention to this, don't pay attention to the million other things, right? And that brings us to lesson number 4, which is AI operations should leverage understanding of intent. Meaning when you build these things, build them so you understand what these agents are trying to do. Don't build them just to be like input, output, because that gives you basically, or basically stimulus response observation, because because that gives you the ability to understand, like whether you're a chatbot, or you're trying to have a conversation, or you're trying to model something so that you can evolve the next cybersecurity system. So all the way from customer intimacy to taking intelligent actions and decisions, build it on deeper models of what's going on, right? And that's something that, by the way, in many systems doesn't happen. It's very surprising. People try to emulate the behavior, but they don't think about modeling the entities. Why is this important? Because of the following graph. So remember when I said there is the stuff that's known good and the stuff that's known bad, which are both easy to classify? And then you've got the stuff in the middle, which is the unknowns, good or bad. Basically, this whole technology, our whole approach was around focusing attention to events that are likely to be bad, allowing it to quickly trace through and see, and then decide quickly whether this is an example for machine learning of a bad event or a good event. And that's how we bootstrapped. And then later, other banks joined in what was called the Cyber Data Alliance to basically start sharing these signals that we were all collecting under this new architecture. This was mostly European banks. So basically, it's all about providing context to that analyst to figure out what to focus on, because at the end, the common sense reasoning, the actual understanding of what's going on, is usually very hard for a computer to figure out, but fairly easy to an analyst if you give them the context, right? They recognize when something is good or bad. And it's very behavior-centric, which leads me to my final lesson for pragmatic AI, which is there is no autonomous AI, and there is no general AI. It is about the hybrid AI, where AI systems help humans perform much of the low-level work quickly and accurately, right? So it's just an extension of something else. We still haven't solved the intelligence problem. But that sort of kind of ends the lessons. The data, however, is super valuable. So here's an example. This is a journey I put the bank on at the time. Financial crime. Financial crime is about detecting when somebody is trying to launder money. How do you do that? Well, you're required by law, like when I do a transfer, say, to Peter, the regulator requires that I know who's sending money, me, who's receiving money, Peter, where, and typically what for. And sometimes what is the source of this money. Sometimes what is it used for. All of this is kind of required by regulators. However, think about this. For most banks, they do this just to satisfy the regulation, file it away, and put it away. However, this information is extremely rich information about my business, right? This tells me that, for example, Usama actually has reasons to send money to the UK, or he has a kid going to school in the US, or he has, whatever, right? All of this are signals that are available. I call it data exhaust, because in most banks, it just goes away. If you actually capture it in these systems, you actually have a huge side benefit for the business, because you're helping enrich the picture of who the customer is, as well as potentially leads to other customers that can join the bank. So I'm going to take a pause here and tell you something even scarier before we go into the applications of cybersecurity. Even the basic thing like a transaction, which in the old days used to be what, when, where, how much, and what payment method. That's it. That's a transaction. Suddenly, with context, you actually can ask questions. What's the context? Where are you? What is around you? Are you moving? Are you decelerating? Are you trying to park? What's the temperature around you, by the way, which is measured by your handy device? Ambient sounds. What is the exhaust around you, basically, the Wi-Fi signals and all of that? There's also graph data here. What is near you? Who is around you? People. Where are you heading to? Because I see your calendar also, right? What's on the way? What are you doing? Biometrics. Are you happy, unhappy, stressed, etc.? All of that being measured by your Fitbit or other devices or your watch. And that brings you to the whole world of IoT, where this is like the Wild West. Because these devices are talking to each other, and they try to talk to you every once in a while. God knows what they're saying to each other. But the bigger question is, how do they even recognize each other? What's a trusted identity? How does this device know who does it report to? Have you checked what your webcam has been doing recently? Right? Very likely it was part of a distributed denial of service attack. used by bad guys to attack somebody that you don't even know, right? And there's a whole new frontier here because most of our security systems are based on this thing we call perimeter. So if I protect, remember that graph? I protect what comes in, and I control it. What happens here is there is no perimeter. The whole notion of a perimeter goes away, so how do you protect, right? And how do you keep things safe? And that leads us to a whole world of like why encryption is a big deal and why identity is a huge deal. So let's take a few case studies here. I know I've been talking too much in the theory. And look at what happens, right? And I'm going to focus on a couple of areas. One of them is critical infrastructure. I don't know how we're doing on time. OK. Greg, how much? I have 50. OK, so I'll finish in 10.
If people want to copy the slides later, would you be able to post
Yeah, yeah, we'll post them.
Site, just post a link to the PDF of the slides.
OK, we'll do. So lots of, by the way, articles on this critical infrastructure attacks. And you may wonder why people attack critical infrastructure. Well, usually the biggest reason, not only is it valuable and it can harm a lot of people, but these things are actually easy targets. Why? So control systems need to be up all the time. So when do you upgrade them? When do you patch them? When do you bring them down? Very infrequently, right? So they're very, very likely to be outdated in terms of patches and security. The traditional solution now requires you to have that internet connection. So suddenly a lot of these things that in the past used to be not connected are now connected, actually, to the internet. So they're reachable. A lot of these systems are old because people get cheap. Like, do you really care whether your water authority is running the latest version of Windows, or what kind of machine is actually controlling all these little, levers there? You probably don't care until something bad happens. And that's what happens here, is these guys are running antiquated systems. And basically, the identification here was that these control systems are effectively super easy targets. So if somebody really wants to attack your power grid or your controllers for traffic lights, etc., it's not a hard challenge. If you look at where they attack in these tiers, right? They can attack on the external facing stuff. They can attack tier 1, which is sort of the guys who run the systems. And they can go all the way down to the system firmware and the I/O. So here's an example. Stuxnet, for example, the way it does the attacks is it relies on getting an infected USB into the system. Now, you could have all the air gaps in the world here. How do they get a bad USB into the system?
Just throw it over the wall.
Throw it over the wall? Yeah, but somebody needs to pick it up. And yes, social engineering is the big one. It's the fancy term. What it means is they find out who the employees are, and they find out their weak points. Are they alcoholics? Are they gamblers? Where are their kids? What do they need? Are they in financial trouble? And you just have a few conversations, and then you finally say, psst, take this USB, stick it in, and all your problems go away, right? And that's when all the problems start, right? Because that USB now is inside the perimeter, right, where you thought it was safe. In fact, it was so safe that you had an air gap, so there's no way to reach it from the outside. And havoc can follow from there. By the way, as I mentioned, this was actually developed first to attack the nuclear reactors in Iran. Then it got used to attack many, many facilities. Black energy is another one that seems to attack almost every layer. And what this chart is showing you, what should be scary here, is the different techniques used and the attacks on multiple layers in different ways. WannaCry actually attacks almost everything except for the tier 0, which is the firmware. Destroyer, the most recent one I've actually looked at is Triton, which actually involves the social engineering to sort of short circuit, but attacks all the way down to the firmware and kind of makes itself permanent, right? We'll talk about some of these examples and what they attack, and it's it's pretty scary. I mentioned this slide I took from Versec because they basically studied a lot of these attacks, and their technology, so there's many ways you can do this. You can look for patterns, you can detect bad stuff happening, or you can analyze execution stacks, which is what Versec does. They'll actually use AI algorithms to actually analyze execution stacks and detect when something is abnormal in the execution stack. So as long as you start from a known state, where you know what the applications are and how they should behave, anytime, it's like a GPS. Anytime you're off piste, some alarm goes up and you can block it. You can actually say, wait a second, this application is no longer behaving the same way, right? So social engineering here to drop files, etc. A technique like this would immediately detect. The minute this attack starts, you actually say, oh, this executable is no longer working the same way. Stop it, right? And that's how you detect a change that happens. Obviously, you have to be in a kind of a stable operating mode. Again, remember my lesson 4, which is model the intent and model what the agents are trying to do. Black energy. This is an attack on our utilities in the Ukraine. Again, if you look at how these things work, there's always an innocuous, weird start. Like this one starts with a Microsoft Word macro, right? That you get pushed in, either through a Microsoft or through an OLE object in PowerPoint. Once it activates, it starts actually looking for ways to kind of embed itself in different parts of the network, and finally takes over. Its target here is just to kill systems. So this one is an example of one which was done just to show that, hey, I could shut down the utility, right? Again, if you were analyzing execution, look at all the opportunities that you can trigger to say, look, execution went wrong. Again, simple trick, which is just simply looking at the execution stack and what's happening at the object level on the executables. With a bit of modeling of how normal is. So you need to have that model. Indestroyer is a whole other one, which is an attack also in the Ukraine on the power grids. Same thing, same basic idea here. Social engineering was the entryway. WannaCry, we talked some about it. It's a bit more complex, but basically, WannaCry relies on replacing certain kind of trusted DLLs, right? So that's why you can't detect it, because it's actually not leaving anything. It's just changing the library. Stuxnet, which is one of the oldest, we talked about this, that it needed a USB to make it inside the network, and then it can find its way all the way down to, and by the way, if you look always at how they execute, they're targeting very specific systems. And typically old systems, well-known systems, well understood, probably not updated. And you know how, once you're there, you can just disable them, pretty much. OK, and this is just a quick ad for them. Versec actually did win the #1 in the 20 hot new security products. But the product here is basically an analysis of the execution stack and what happens when you return from function calls. That simple trick can actually detect a lot of stuff deterministically. You don't even need to know what is bad, just that it is bad. It is different. So summary. Weaponization is now going against normal users. So this is becoming like a scalable cybercrime. The bad guys are not at risk. This is what's scary about this. They work in comfort and optimize their bad products, typically protected by nation states who are actually funding them to do the work, and typically helping them, sometimes inadvertently, like Stuxnet. There's an increased sophistication of these cyber attacks, so they're more targeted. And there's a new generation of them, which is much harder to track and detect, right? Because they don't leave droppings behind. I don't know why this thing gets stuck. OK. Much more difficult to track and detect, of course. Unknowns create the uncertainty, right? Stuff just, you got to let stuff through. It assembles into really bad stuff inside, like I showed you in some of these attacks. I know we went through them fast, but I wanted to make sure to wrap up within a few minutes. This actually creates a whole snake oil market where fear, uncertainty, and doubt lead to basically overprotection of the known bads, right? If you've got a tool that works in the known bad case, which is usually very easy to handle, you go out there and you sell it to everybody. And you tell them, if you don't buy it from me, you're negligent as a Seesaw. And what happens there is people overbuy stuff that's protecting them against the known bad stuff under protection of the unknown, right? Because that's mysterious. Today, the following is true. Because we haven't evolved our thinking to say the perimeter doesn't exist in this new connected world, once you penetrate the perimeter, the game is over. You're pretty much lost, right? So today, it's all architected around protecting that perimeter, and that's a very bad architecture, by the way. One of the early exercises I did at Barclays, and my job was not the Seesaw, but I walked in and I showed that if you unplug the Polycom machine in a conference room, which is connected to the internet, that's actually on the corporate net. And from there, I plug in my computer and I could hack into a mail server, for example. Why? Because they assumed that once you're in, everything is secure, right? And the first thing I did is I actually hacked the email of Trolls and sent him an email from himself saying, hey, check this out. And I needed him to testify that I was doing good here and I wasn't breaking laws, because a bank typically can fire you over even showing them this stuff. Methods that use AI and ML are becoming a necessity in this space, because basically the space is exponentially huge of all the unknown stuff, and you need to employ these techniques to help the detective skills basically scale, right? Help you detect these incidents and then help you investigate them in context by grabbing all the data around them. So it's all about, I mean, today I think the hardest systems are the ones that enable agility and a quick ability to kind of detect patterns and follow up on them. And data fusion for me is the hybrid sort of human big data AI approach that looks most promising in this space, because it's basically a space very rich with data. Data is AI, data and AI strategy. Data is the main asset. Remember, we don't have new algorithms, we just have more data, so make sure you can manage the asset. AI and ML cannot work effectively without data. AI and ML can actually enhance your data, so you can have even better data assets. Your digital transformation must be linked to a data strategy and an AI strategy that says, here's why I collect this data and here's how it gets used. And then you have to get clarity on the cloud. This is a whole other debate that we won't go into today, but there's a whole other talk around cloud. Remember to always focus on narrow domains, right? Remember my 5 lessons? Reduce the problem domain to be as narrow as possible, because that's your only hope to solve it, because then you know everything about the world, which is necessary. Lesson 2 is data is a huge enabler, so you have to have a way to capture it and manage it. AI and ML are very finicky, so you must feed them data correctly, which means you have to have the flexibility and the ability to capture all sorts of data. AI operations should model the processes and aim at understanding intent, because if you understand intent, you can then truly do smart actions down the road versus just stimulus response. And the final one is don't rely on a general AI. It does not exist, at least not yet. So it's all about how do you make the hybrid AI, human and AI, work together effectively. With that, I wanted to spend, this is in the Department of Announcements, a few words on an effort we're running called the Initiative for Analytics and Data Science Standards, and is in collaboration with Hamid Hamuchu, who's in the audience, and actually Don Pepper is on our advisory board. Data scientists. You think you know what a data scientist is. Here is the rate of growth of people who call themselves analysts who show up on Kaggle, right? And the CAGR here is 117%. So we're up to about 1 million people in 2017 who called themselves analysts. So do you think everyone understands the same from the term data scientist? And of course, because data scientists are well paid and in high demand, everybody claims they're a data scientist. But we did a bunch of research, and I'm going to share with you just a teaser here. Hopefully, we will have this panel and presentation in a month or two here, where we will discuss this in detail. Here are 3 people. This is from LinkedIn, so public data. 3 people at Facebook who call themselves data scientists. So if you look at each one of them, it says data scientist at Facebook. Number 1, if you look at their background and what they work on, it's almost nothing in common. So if you look at this person has a PhD from North Carolina State University in industrial and systems engineering. This person has gone to the New York School of Business, Stern School of Business, Bachelor of Science. This data scientist has actually studied, what was it? Sustainable development in business. Beijing Language and Culture University, right? So you look at their backgrounds and you say, same position, same company, very, very different backgrounds. And if you look at skills, what they claim as their skills, no interaction. All useful, by the way, but no intersection in the skills, right? So completely different entities, but all call themselves data scientists. So we created this initiative where because we want to actually a whole bunch of a bigger group of people and kind of publish some of the results from the workshop around these initial definitions. And it's the very memorable link KKJP9X7. but you will have access to these, and you can search on it online or search on IADSS. We would love it. If you're a data scientist and took the survey, it would help us a lot also, and it will give you some calibration information back. I have my contact information. And we are hiring big time. So here are the links. With that, I don't know if we have time for questions. OK. So questions? Yeah, Peter. And if you use the microphone, I don't need to repeat the question.
Just put that QR code back up so we can respond.
Ah, yes, good point.
Hi, I have a question, but a few real brief comments. One, I'm a little surprised. First of all, it's a great talk. It was more of an introductory course, I think, than simply a talk. So it's really good. I'm surprised you didn't mention another enabling factor of big data, of the deep learning, machine learning revolution. Besides what Peter Norvig said, I think it was also the surprising or accidental discovery that GPUs and now TPUs were like perfect for doing the processing in neural nets. So sort of another advance that nothing to do with AI, current machine learning possibly. The other quick comment is I don't think expert systems died. They simply became, like many computer science stuff that used to have separate names, embedded. So for example, TurboTax is a giant, widely used expert system in many respects. And final other comment is I think it was spelled Tolerant.
I misspelled?
Tolerant.
Oh, OK.
It's ER, not AR. The question I had was, you brought up one really important research topic in AI, to do what you said, which was intent recognition. A very hard problem in both directions, human intent recognition of intelligent machine agents and machine recognition of human intent. I was wondering if you thought at all about what other, in the research realm, topics do you think are important to enable the kind of merge of AI, big data, and cybersecurity that you were talking about? For those of us who are still funding and enabling the research community, what should we fund in that area?
I think, by the way, I mean, great questions. So I don't know how to respond to most of them. I'm not going to repeat the question, but Well, I will repeat the last part, which is what areas of scientific research do we think merit further investment and attention to enable this kind of AI and cybersecurity merger? And I think big time, anything to do with machine learning, especially machine learning in the presence of graphs and connected entities. Any kind of our ability to actually put together these multidimensional time series into something understandable and manipulatable is very hard to non-existent in terms of tools that help us capture it. So analysis algorithms and tools that can understand that. The third one is this whole area of, which is an old area, but still deserves a lot of attention, kind of where do you focus your attention? Out of all the possibilities, how do you quickly, A, detect things that are worthy of focus, and more importantly, quickly abandon them or abort them once you decide this is not interesting. So those would be like the ones that come to mind just from the applications and the challenges we faced with the data fusion work. But to me, in general, that whole space of, like, if you ask me today, is there a reliable machine learning algorithms that I could use on this variety of data, on a data that has a social and or professional graph, structured data, and a bunch of images and or voice recordings or whatever? None exist. So the whole gamut of attribute definition, attribute extraction, deciding the right representation, none of it. It's all like starting from scratch for researchers or for practitioners who are trying to do any damage against these challenges.
So learning from unstructured data?
I would say a mix, the mix of data, structured, unstructured, and graphical. So for example, a graphical databases got some attention in the database world, got very little attention in kind of the learning side of it. And then you find learning algorithms that work on graphs, but they don't work on graphs in the context of other stuff. So a lot of this, the true leverage of the variety of information and getting a signal out of that is unaddressed in most cases. And most algorithms end up being very simplistic, like they project it down to some highly structured, understood space and try to solve a problem, and then claim some success. But good question. Other questions? Anything I said that was controversial? Yeah?
Like the whole ML, AI stuff.
Microphone.
The whole ML and AI thing, could that be understood as something underneath operations research?
I think operations research, a lot of the problems in operations research are optimization problems. And the fundamental problems in AI and machine learning are optimization. Now the trick is how cool and varied is your optimization algorithm? How capable is it of dealing, like if you asked for a optimization algorithm that dealt with, flat measured data, especially if it's numeric, very easy. Tons of algorithms exist. The minute you vary that one and say, oh, now these structures are nested, or some of them are not numeric. They're now symbolic. Or I add a graph to them. Or I add a different form of sequence, another dimension. Everything breaks down. No known, well understood, reliable optimization techniques. So a lot of these things wind up in OR. By definition, the art would be, can I reduce it to a simple problem where an classical optimization algorithm works and then show I can solve it reliably? In this new rich world of kind of variety of data, et cetera, there's nothing, nobody knows what to do. A lot of these OR people, if I throw a terabyte at them that has a social graph and a few images, I think they'll be dead in the water. Most of us would, by the way. And what's really scary is it's very easy to get that kind of data today. Like you give me any database, highly structured, and in no time I can make it a big database. by adding in the variety, right? Social graph, professional graph from LinkedIn, all sorts of other information, all sorts of search results, all sorts of videos, audios, etc. There's a question here and there.
Back in the 1980s, fast machine was a 1 megahertz machine, which is where you talk about the first and second winners. You also
I think they used to be in the kilohertz. I'm that old.
Yes.
In the 80s, yes. Yeah.
You were even slower.
Yeah.
You also talked about logic and probability inferencing not scaling at that time. Isn't that really a little disingenuous? Because at the time there wasn't enough horsepower to make things happen. There were also these machines had 64K or 128K.
Sure.
That's
So unfortunately, the jump from kilohertz to gigahertz and maybe teraflops sometime soon is not enough to even address exponential, let alone undecidable. So in logic, the biggest problems were decidability problems. Like theorem proving is hard. It's not just exponential. It's harder than exponential. Most of these search problems, optimization problems, are actually exponential in their nature, right? Unless you have quantum computing and you can guess. So yes, speed helps, but very little in this against the exponential. And that's the problem.
even with algorithms like A-star search.
Oh, yeah.
That go after best first search.
Best, yeah, I mean, A-star is a special kind of best first with the heuristic, but, and it can help. In many instances where you know enough about the world, it can help a lot. That's how chess players can beat most humans in look-ahead search. However, the kinds of problems we're talking about solving, like we're communicating right now, and I doubt that there's a computer on the planet that can keep up with this conversation we just had. It's that bad, right? After 50, 60 years of hard work against the same problem, right? Natural language processing or understanding has been around for that long. So I think the speed helps. I think having more compute helps. But the real breakthrough has been having more data. Having data points that tell you what behavior should be. They're kind of guideposts. I don't make any claim that the solutions you get have anything to do with how humans do it or with true intelligence. But they actually do work, practically. There was one back there.
You talked about your replacement with data fusion.
Yeah.
And I'm curious to know, with the democratization and commoditization of some of those technologies available with the cloud providers now, is it possible for small scale companies to implement something like that? Or is it still, would they still be stopped from doing so by not having the human power to be able to do these things?
Yeah, great question. So with the availability of these tools now on cloud, and Microsoft has the machine learning cloud stuff, and I'm going to share with you a story which is, I found it funny at the time, but it kind of describes sadly our state of affairs. So utilizing a lot of these algorithms requires a fair degree of sophistication to understand what they do and how to use them. Because it's garbage in, garbage out if you don't understand what the algorithm is doing. Back in the late 90s, I had this very interesting conversation with the guy who was running Microsoft Office around embedding analytics tools in Excel. His name was Steve Sinofsky. And he listened to me politely because Bill Gates told him to listen. And when I finished talking about what we can do in embedding data mining and machine learning in Excel and showed examples, and I worked out, he said, are you done, Usama? I said, yeah. He said, OK. would you care to guess what % of users of Excel use Excel with a calculator on the side because they don't know it even has a plus function inside it? And the number threw me out of the room, 98%. Right? So the problem is, a lot of these tools that get used in automation and all that, it's the simple stuff that gets used for natural reasons because people get the simple stuff. Excel gets used as a list management. Very few percentages use Excel actually for computing and actually doing spreadsheets. Most of it is managing lists and looking up stuff and recording stuff. So to me, that's the problem we face right now, is we don't know. These algorithms are unreachable to the majority of the population. So you need the experts, nowadays called data scientists, who actually understand enough. And this, I would add this problem to Peter's list of problems to be solved, which is representations. What are the right representations? I mean, the whole problem is you take the inputs, the data space, and what do you map it into so that the problem is now solvable and addressable by some of these capabilities and algorithms. And that's where we get stuck. So yeah, unfortunately, faster processors and available cloud algorithms don't help us much. We still need human wisdom to help us figure out how to apply this stuff correctly, as of today. Now, we haven't gotten to the point where there's a box and I can throw it at it and it'll figure out what to do. People try to do that, but it's very hard. Yeah?
Thank you for your presentation. Very interesting. Very informative. The question at the end, maybe I missed a lot. So how we actually will apply the crime in cyberspace and information space, because machine learning just helps us to solve knowledge. And we could solve unknown. We don't know, we don't know. AI is a big question. You said we don't know what the AI is. So what's actually
Yeah, so the excellent question. So, you know, since AI is so hard to make work and machine learning is good at stuff that's known, and we said that a lot of the unknown is a problem, how does this technology help us? And the hypothesis in this talk is that with data fusion, i.e. the ability to bring the data together with some rudimentary capabilities to detect that something is suspicious, and an ability to give a view to the human, to allow them to quickly judge, is there something bad here or not, is the beginnings of how. So how the cycle starts is as you start doing these, as you start processing these events by humans, because you give them enough context, they can give you the proper classification. Because they gave you the proper classification, you now have reliable training data. And reliable training data is usually the hardest thing and most expensive thing to get. Once you have it, you now have started the virtuous cycle. And now you can actually start building better and better recognizers. And that's how these algorithms work. We need them because the space of possibilities is so huge that it's hard for a human to navigate. But for algorithms, be they AI and or AI combined with ML, to navigate, detect, and then ask the question, does this warrant more attention, yes or no? And if so, what happened? That's how you start building up your defenses. And that's how as naive as that sounds, that's how we started with data fusion. And it's amazing how much that powered the personnel who are doing the security investigations. It was a huge, it's a big shift, a qualitative shift in productivity and ability. And then, when you add the sharing across the banks that say, I spent some energy detecting the signal, if you see the signal, that is bad, and now it's shared, that is how you start doing it through triangulation and kind of swarm effect to solve the problem. Very practical. It does not give you a theoretical solution. I don't have a theoretical formula for how to solve these problems, unfortunately. But I do have some practical engineering approaches. Yep. Are we done? Ah. We have to be done? He's
Question? Okay.
Why all the hype from high-profile figures like Elon Musk or Stephen Hawking when it's completely disconnected from the people that are inventing this technology?
I don't know. You have to ask them. I have no idea. I mean, I do disagree with their statements.
Can I ask one question?
Yes.
You talked a lot about the four notch model of security. You all did it at one place and you all started to protect the four. What about the blockchain approach of having data copied on a large number of unknown nodes? Attacker doesn't know where to attack this. And even if they attack one or two nodes, other nodes will come to consensus about what to do data. So what
Yeah.
is that different approach of?
So I would say there, it's not, the blockchain does not do anything for the distribution. The blockchain does something towards the authentication and identification, which is important. That's a big part of the cybersecurity puzzle. But yeah, I mean, my answer to that one is today, getting the data in one place where it's actually analyzable has been challenging enough. Coming up with algorithms that work on the data in the wild before it's assembled and understood, that's an even further challenge. I think it has to go that way. In this world of IoT and no perimeter, that is the way to go eventually. But today, we don't even know how to start to address that problem. Last question, I think.
Okay, my last question is, this is the last request for Amy.
This is the meta question. Okay. All right.
Let's give him a round of applause.
Thank you.